Okay, good morning to all of you.
Good morning, sir.
With that up to 1.3, that all we have studied, that is all about propositional logic. Today we'll start a different section, that is 1.4. That is all about predicate calculus or predicate logic. We'll see that. That is your start of section 1.4. And that is predicates and quantifiers. That means that is you can say predicate logic or predicate calculus. In predicate calculus, we'll always deal with predicates, another is quantifiers. That means in propositional logic, that means what? The area of logic that deals with always propositions. That is, we have studied 1.1, some applications in 1.2 and 1.3, some logical equivalences. That deals with always propositions. That is a propositional logic or propositional calculus. In this section, we will deal with predicates and quantifiers. That means the area of logic that deals with predicates and quantifier is called the predicate calculus. You can see the area of logic. That's the chapter logic that deals with predicates. What is a predicate? We will see later. Predicates and quantifiers. It's called predicate calculus or predicate logic. Okay. Then see what is a predicate from English sentence or grammatical perspectives. See what is a predicate from English sentence in the sense of English or grammatical meaning or perspectives. Meaning of predicate. Predicate is a part of a sentence That means it is a part of a sentence or clause that involves a verb and the fact or opinion stating about the subject or stating something about the subject. Let me see. The statement is given Aditya is a student of KIT. Then tell me in this sentence, what is the subject? Aditya is a student of KIT. So what is the subject here?
Aditya.
Aditya. Okay. So in this sentence, Aditya is the subject. Okay. Then rest of the part, except subject, involving a verb and stating something about the subject. What is that part? This part. Is that is the verb is a student of kids. So this part is called the predicate. That means in an English sentence, so in an English statement, that is subject part, that is the predicate part. Okay. In case of propositional logic, we cannot express all those statements. In case of mathematics or any other subjects, we cannot express the meaning of all the statements or propositions in propositional logic. That means, see one example. That means propositional logic cannot able to express all the meaning of all the statements in mathematics. Mathematics or in computer science or any other subjects. Or any natural languages. In some cases, propositional logic fails to express. See one example, you will get it. Let the proposition are given as P be the proposition that is given. All the students of computer science engineering of kids are studious. Q be the proposition. Ayush is a student of CSC of kids. And R is the proposition. Ayush is studious. Then tell me, if you are using some propositional logic, is there any proposition logic using P and Q, can you conclude R? Then what is that propositional logic or propositional rule? Means we cannot say. We cannot use your propositional logic. That means there are no rules to use propositional logic, so that we can say that R, what will be the truth value of R depending upon P and Q. We cannot say. That means, see, there are no rules of propositional logic, which allows us to conclude the truth value of R using P and Q. Then tell me, but from the English meaning, tell me if P and Q, when R will be true, what is the truth value of R? If P and Q are true, P is true, that means all the students of CSC are studious. Q says that I should be a student of CSC. Then R I should be studious. That will be true or false?
True.
True, because from the logical meaning of the sentences, it is given all the students. It is given all the students. Ayush is one of the students among them. So, as all the students are studious of CSC, so as Ayush is a student, then Ayush must be studious. That means when by logical we can conclude that when P is true and Q is true, R is a proposition that must be true. However, we logically conclude that from the meaning of the sentences, if P and Q are true, then we can conclude that R will be true. So, if we introduce some predicate logic to express the meaning of these type sentences or statements in mathematics, in your computer science, or any other fields also, we can more precise the meaning of the propositions or statements. Okay. See, that also we know that. See, the statements involving variables such as x greater than 5, x equal to y plus 10, x plus y equal to 5z, x is intelligent. These sentences are, what is the truth value of these sentences? X greater than 5, it is true or false?
Sir, it is not a
Sir, it
proposition.
is
It can be
yes,
true.
sir.
Yeah,
Not a proposition.
it is not a proposition. All the sentences x equal to y plus 10, x three variables x plus y equal to 5z, x is intelligent. So all these sentences are neither true nor false. We cannot say. That means these statements are neither true nor false. Until what? If we assign some specified or specific value to x, then it becomes a proposition and it must have a truth value. That means unless the values of the variables are specified. That means, see, that is important. The values of the variables are specified. That means until we are not if we are not assigning some specific value to the variables x, then we cannot say that is true or false. If we assign some specific value to x, then it becomes a proposition, then it must have a truth value. Okay. Then some notations are there. We denote the statement. The left statement is x is greater than 10 by notation is predicate p of x. What is p here? That is the predicate. P stands for predicate. Then what is the predicate here? X is greater than 10. What is the subject here?
Greater than 10.
Yeah, is greater than 10. Is greater than 10. That is the predicate part from the English sentence only. So what is x here? X is the subject or is the variable here. So the statement is x is greater than 10, that is noted by p of x. The notation is p of x. That is, you can also read this p of x, or that the meaning of p of x is value of p at x. Value of the propositional function p at the point x. That means p of x, that stands for p, value of propositional function x at p. You can read this, or simply p of x. P stands for predicate. Then that we have already discussed, when we are assigning some specific values or particular values to the variable x, then the predicate p of x, that is c x greater than 5, x equal to I plus 10. All these statements are not propositions, but that are the predicates. That means, what is predicate? We will see once the value has been assigned to the variable x, then we can say that the predicate p of x becomes a proposition. And as it is becomes a proposition, then it must have a truth value. Just see that particular example. X is greater than 10. So it is the predicate. By notation is p of x. So it is not a proposition. If we specify some particular values to x, that means 4 greater than 10. It is a proposition or not?
Not a proposition.
No, it is a proposition.
It's a proposition with false.
Yeah.
Value as false.
Yeah, truth value will be false, but it will be a proposition. That means when we are assigning some particular value to x or specifying some value to x, then it becomes the predicate x is greater than 10. That becomes a proposition and it must have a truth value. 15 greater than 10. It is a proposition. It is a truth value is true. That means like this, when we are specifying some particular values to the variable x, it becomes a proposition. That predicate becomes a proposition and must have a truth value. Now we will see the proper definition of a predicate. What is a predicate? A predicate is just statement which contains variables. Variable or variables, and it may be true or it may be false. That always depends on the values of the variable. Thus you can write variable or variables. That means, see, what is a predicate? Predicate is a statement which always contain variable or variables. That is important. It must contain a variable. It may be x, y, z, whatever the values. It must contain a variable. Then that predicate, you can say it is true or false. That always depend upon the particular values of the variable. Before assigning the particular values, we cannot say it is a true or false. When we are assigning some particular values of x, then we can say that it is true or false. So that is the exact meaning of predicate. Okay. Then see what will be a domain. Domain or domain of, it is also called domain of discourse. The same, just notice domain. Say, domain means in the domain of a predicate. Domain of a predicate. That means when we are taking the values of x. So where we are taking the values of x, what are the possible values of x? So these all the collection of possible values of x. That set is called the domain of predicate or domain of discourse of that predicate. The domain of a predicate is a set or collection of all possible values of the variable that may take. All the possible values of that the variable may take. That means if you collect the set of values of x, that is a set of possible values of x, for that particular values, the predicate are going to become propositions, or it may have either true values, true or false. For that set of values of x or the variable, that set is called the domain of the predicate. Okay. Consider the predicate that is x square greater than 10. Predicate that is given notation is P of X. P of X, that is the predicate, not proposition, predicate, X square greater than 10. Where the domain consists of set of integers. Domain is Z. Z means that is the set of integers. And the truth values of P of 2, P of minus 5. So according to question, what is given? Given that predicate P of X, that is given X square greater than 10. That is not a proposition. That is a predicate X square greater than 10. In propositional logic, X square greater than 10, that is only not a proposition, but we can say that X square greater than 10, that is a predicate P of X. Okay. So in that P of case, we are going to find the truth values of P of 2 and P of 5. Where your domain, you can notate domain D, that equal to given Z, that is the set of integers. All positive integers, 0 and negative integers. Okay. Then tell me what will be P of 2?
So false.
Sir,
Okay. P of 2 is 4 greater than 10. It is true or false?
sir, it is false, but it is proposition.
Yeah, it will be a proposition, it will be false. So what is the truth value of P of 2? So we can, if we are specifying some values of X from the domain, so first see, 2 belongs to Z. So always the values of X that belongs to the domain Z. That is important. Domain D. The D may be Z, D may be set of real number, D may be a particular set containing 3 elements, 4 elements, it may be infinite set also. So P of 2, that is 4 greater than 10, so that is false. So like this, P of minus 5 also belongs to Z, so we can take X as minus 5. So P of minus 5, it is true or false?
True, sir.
Yeah. P of minus 5, yes, that is 25 greater than 10, so it is true. That means from the predicate, if we assigning some specific values, we can say that it is true or false, or all are propositions. P of X is not a proposition, but P of 2, it is a proposition. P of minus 5, it is a proposition. Okay. Then come to quantifier. Quantifier, that is related to the word quantity. Quantity, that is from quantity. Quantifier comes from the word quantity. So quantifier, in the meaning of English, quantifier is the determiner or you can write it pronoun indicative. Pronoun indicative of quantity. Okay. See, quantifier, let me see. When you are using predicates calculus, the aim of the predicate calculus is from the propositional function of propositional logic, which are not propositions, where there is a way to create the propositional function to a proposition by using predicates or quantifier or whatever the weights. That is a way. That means there is another way, that is using quantifier. One part is, that is predicates. There is another way to create a proposition from a propositional function. Okay. Then tell me some English words that represents to quantity. Tell me some English words that represents the quantity. Okay, see, the words all represents to quantity or not? All. You can write some, few, many, none. All these words represents to quantity. These all are used in quantification. Okay. There are in quantification or quantifier, there are two types of quantifier. We are going to deal with two types of quantifier. One is universal quantification, another is existential quantification. Okay. First one is universal quantification. See, universal quantification means all the words, all, some, few, many, from these type of quantity or quantification, which what are the meaning of universal quantification? See, universal quantification comes under this quantification, which tells us that a given predicate P of X or given predicate is true for every element present in the domain or every element under consideration. That means for all possible values of the variable. Predicate is true. That means, see, the quantification goes under universal. Those quantification says that or tells us the predicate will be true for all the elements that are present in the domain, or for every element taken into that domain. So that comes under universal quantification. Okay. Another quantification is existential quantification. Existential quantification. Which tells us that there is one or more elements for which the given predicate is true. And means, see, one is universal quantification, another one is existential quantification. Universal quantification says that the predicate is true for every element present in the domain. Existential quantification says that or tells us that there exists at least one or more element for that particular element, the predicate will be true. That means existential, that means there exists. Universal means for all. Okay. See what is a universal quantification, then see the proper definition of universal quantification. Okay. The universal quantification of a predicate P of X is the statement. The statement is P of X for all values of X in the domain. That is the meaning of universal quantification. See, universal quantification of P of X, that means Px will be true for all values of X that present in the domain. The notation, you can use the notation for universal quantification for all X, P of X. This is the notation for universal quantification. Universal quantification of the predicate P of X. That means, see, if it is written for all X, P of X, that is a symbol for all X, P of X. That means you have to understood this. This you can read this universal quantification of P of X. That is the same as for all X, P of X. Here, for all symbol, this symbol is called universal quantifier. That represents for all. So for all symbol, that symbol is called, or that quantity that represents the quantity for all, that is called universal quantifier. But for all X, P of X, that notation, that is the universal quantification of the predicate P of X. P of X is the predicate. If you are using the notation for all X, Px, that is the universal quantification. Okay. The universal quantification that is for all X, P of X is true. And tell me when it will be true. When the universal quantification for all X, P of X, it will be true. I have already discussed about that. Universal quantification, that means predicate is true for every element. That means universal quantification for all X, Px, that is the quantification. This will be true when, or you can write if and only when, if the given predicate P of X is true for all values of X present in the domain. And when it will be false, when it will be false, the universal quantification for all X, P of X, it will be true when the given predicate P of X is true for all the possible values of X, or for all the values of X that are present in the domain. Then tell me when this quantification for all x px will be false.
When the x will be not present in the domain of the PS.
No, that means
Sir, when it is true for only one or more elements, for not all the elements.
yeah, for not all the elements. See, not all the elements. That means you are getting at least one element, so that for that particular element the given predicate is false. If you are getting at least one element present in the domain, but for that particular element p of x is false, then we can say that the quantification for all x px, that is false. That means that will be false if there exists some element or at least one element in the domain for which the given predicate p of x will be false. For true, it will be true for all the values of x in the present in the given domain. But when the quantification for all x ps will be false, what is the condition? If you are getting at least one element present in the domain, such that for particular domain the given predicate p of x will be false, then we can say that if the predicate is false for at least one x, then for all x px that will be false. That particular element for which the predicate p of x is false, that is called a counter example of for all x p of x. That means if it is true for all the x except 1 or 2 or 3, if you are getting a particular x so that the given predicate is false, that particular x is called the counter example for universal quantification. Okay. Let p of x, that is given, be the statement x plus 1 greater than x, that is given. Then what is the truth value of the universal quantification? Universal quantification, that means for all x px, where domain is important. Domain must be given. Domain consists of all real numbers. Okay. That means according to question, what is given? That is given that predicate p of x. So p of x, that is given as x plus 1 greater than x. So that is the given predicate. Then tell me, also domain. Domain is given D. Domain D is given set of consist of all real numbers. That means that is the set of real numbers. You can write it capital R. Okay. Then tell me, for all x px, it will be true or false?
So true.
Okay. Why it will be true?
Sir, because if we set the values negative also, it will be true. For 0 also true, and for positive numbers also it is true.
No, you cannot show. You
Sir,
cannot.
because in LHS one is adding, it means
Yeah.
it always greater than.
Okay, it is always greater. That means see, but always remember what is the domain. Domain consists of all real numbers. You have to focus on that. If when it will be true, what is the condition? If the given predicate is true for all the elements present in the domain. So domain is set of real numbers. So you have to check that the given predicate, that is x plus 1 greater than x. If it is true for all the real numbers, then the quantification will be true. Otherwise, it is false. That means you can observe here. Here the p of x, that is x plus 1 greater than x. It is true for all real numbers. You have to write the all real numbers, not positive integers, negative integers. If it is also z, it is also true. Yes, it is given that real numbers. You have to use the term or what real numbers. That means the given predicate is true for all the real numbers x. That means all values of x in R. R means that is the domain real numbers. That means we conclude that the given predicate p of x, that is x plus 1 greater than x, it is true for all real numbers x. So as it is true for all real numbers x that are present in the domain R. So we conclude that the given quantification or universal quantification, what is that? For all x, p of x, that is the universal quantification, is true. That means for all x, that is the standard notation of universal quantification for all x. P of x. P of x may be different to different problems. Here P of x is x plus 1 greater than x. Domain is set of real numbers. So universal quantification for all x px, where P of x is x plus 1 greater than x. It will be true when domain is set of real numbers R. Okay. Take one more example. You can take also P of x, Q of x, R of x also. Let Q of x. You can write P of x, in some cases Q of x also, no, predicates. Statement that is x less than 10. Then what is the same problem? What is the truth value of the universal quantification for all x, Q of x? Where the domain is set of real numbers, consist of all real numbers. So according to question, what is our predicate? Predicate Q of x, that is given x less than 10, and domain D is also given set of real numbers. Then tell me the universal quantification for all x qx, where qx is x less than 10. It is true or false?
So false.
Yeah, it will be false. Why it is false?
Sir, because it is not true for all the real numbers.
Yeah, it is not true for all the real number. That means not true. You have to find a counter example. If there exists a counter example such that the Q of x is not true, then you can say that the whole quantification or universal quantification is false. If it is true for all the values of x that present in the domain, then it will be true. That means here q of 12. What will be q of 12? That is 12 less than 10. 12 belongs to R, but 12 less than 10, it is false. So q of x less than 10, that is predicate. That is not a proposition. When putting x equal to 12, so q of 12, that is 12 less than 10, is false. That means x equal to 12 is a, you can say that particular values of x, that x equal to 12, is a counter example. Counter example for all x, q of x. So that means the given predicate q of x is not true for every value of x belongs to R, or every real value of x. That means we conclude that as it is not true for all the values of x, or for every values of x for real numbers, thus we conclude that the quantification that is for all x p of x, that is given q of x, is false here. That particular example is called counter example. Then tell me same problem for all x qx, x less than 10. If the domain is 1, 2, 3, 4, 5, domain is 1, 2, 3, 4, 5, then this for all q of x, that is true or false?
So true.
It will be true. That means the same problem the same example, but different domain. Let domain D contains elements 1, 2, 3, 4, 5, and 6. Let's. So this, the same example but different domain, makes the quantification for all x q of x is true, where q of x is x less than 10. That means see, x less than 10. What are the possible values of x? X may be 1, x may be 2, x may be 3, 4, 5, 6. Not beyond that. That means possible values of x are that always from the domain. So for all x, q of x is true here. 1 is less than 10, 2, 6, up to 3, 1, 2, 3, 4, 5, 6. All the values of x, all are less than 10. That means here you can say that the quantification for all x qx will be true. Makes the quantification, universal quantification, true. The same example. That means always domain is important. Okay, let's stop here. Remember, domain is important. From the domain, you can conclude the same quantification. That may be true, that may be false. That depends upon the values of the x. Okay. There are some one more quantification, existential quantification. We'll see in the next class. Okay, just wait.